So if the Bohr model of the atom explained everything, then actually chemistry would be pretty simple. It's simply a matter of electrons being closer to or further away from the nucleus. It gets a little bit more complicated than that, and a lot of that has to do with what we call quantum mechanics, quantum rules, quantum physics. Again, going back to this idea that Max Planck had about energy comes in these packets. So let's talk a little bit about some of these quantum rules. Okay, so the first thing that we need to talk about is a guy named de Broglie. Now, de Broglie was working off of some of the same stuff that Max Planck and Einstein were working on. You'll recall that Einstein said that maybe light is both a particle and a wave. It behaves like a wave, and sometimes it behaves like a particle. Even though typically we think of light as a wave, well, de Broglie's like, well, does that work the same for all matter? Do particles also behave like waves? And it turns out that for very small particles, they do. So de Broglie showed that electrons could behave like light in some cases, like a wave. And as waves, they could only exist in certain places around the nucleus, so that helped back up some of the stuff that Bohr had been saying, and they can overlap. And because they can overlap, that means in some places they can exist larger, or rather, there can be more electrons there. And in some places, they can cancel out, and there will be fewer electrons there. So, where exactly are these electrons? Well, now it gets even more confusing. We've got a guy named Werner Heisenberg. Not the same Heisenberg from Breaking Bad. That guy's named after this guy. And Heisenberg was doing some work, and he figured out you cannot know both the position and the speed, the velocity of an electron. And in fact, this is true for any particle. The more you know about the electron's position, the less you know about where it's going. And the more you know about where it's going, the less you know about where it is. It seems very odd because you can think, well, I know where my car is, and I also know how fast it's going. Well, a car is very, very big, and really that's just a rough estimate. If you were really to go down and see where all the atoms of the car were, it would get a lot more complicated. When we're talking about electrons especially, you can't know both where they are and how fast they're going. To add to the mix, a guy named Erwin Schrödinger was working with something even stranger, with these wave equations. And he found out that since these electrons are behaving like waves, we don't actually know where they are. When we looked at the Bohr model of the atom, we looked at these circles around an atom like an orbit, like it was a planet going around the sun. And with a planet going around the sun, we know exactly where that planet is. It's somewhere on that line. With an orbital, it's more fuzzy. An orbital is a three-dimensional region around the nucleus that is probably where the electron is. There's in fact about a 90% chance that the electron is somewhere inside that shape. The easiest shape of an orbital, an s orbital, is going to be a sphere. Nice and easy. A lot of the shapes, not as nice. We'll take a look at those. Okay, so combining the ideas of these three guys, we've got the idea now that electrons can be found in orbitals. But before we can talk more about them, we've got to talk about how to name them. And we're going to name those with quantum numbers. First of all, might as well say, why do we care? Because the chemical properties of an element depend on where we find those electrons. So again, these quantum numbers, they're going to specify the properties of the atomic orbitals and the electrons inside of them. First one, nice and easy, it's called the principal quantum number. Oftentimes that's specified by the letter n. These have to be positive integers, and you'll remember from math that's 1, 2, 3, so on. This is going to represent the energy level, sometimes called the shell of an energy shell of the orbital. 1 is closest to the nucleus, 2 is further out, 3 is further out than that. Now it gets a little bit more funny. The second quantum number is angular momentum, oftentimes referred to by the letter L. The possible numbers for this are ranging from 0 to n minus 1. So if you're in the third energy shell, you can have 0, 1, or 2 for this. This value, this angular momentum value, is going to define the shape of the orbital. 0 is going to be a sphere, nice and simple. 1 is going to look like a dumbbell. You've got 2 bulbous parts here. For 2, that's oftentimes referred to as D. That's going to be a double dumbbell. You've got 2 interacting sort of at perpendicular angles, all except for this one right here. You may be wondering why there's 1, 3, 5, 7. We'll get to that in just a minute. And for an L value of 3, which would be a shape known as F, it gets all sorts of weird. Those are very hard to describe. I know you're lost. Bear with me. We'll work with this in class. It should make more sense there. You should also be following along in your book. This is chapter 4 again, okay? The third quantum number is called the magnetic quantum number, m sub L. This can be a number between negative L and positive L. Has to be between those two. And what it is going to be, it's the orientation of the orbit in 3 dimensions. Notice here, for a sphere, there's only one possible way it can be oriented, because it's a sphere. It's got the same symmetry on all sides. For this p orbital here, you can put these 2 lobes one way, or another way, or another way. That's why we've got 3, and then 5, and then 7. Again, we'll play around with this more in class, but you may want to start to look at these shapes so you get an idea of what's going on. The fourth quantum number is called spin, m sub s. Only 2 numbers allowed here, positive 1/2 or negative 1/2. Think of these as the electron spinning up or spinning down. They don't really spin. It's a number that has to do more with the magnetic state of the electron, but we call it spin, and it may be simplest for you if you think about it as the electron spinning. Now, why do we care about this spin? Well, because each orbital can only hold 2 electrons, and their spins must be opposite of each other. So one has to be plus 1/2, one has to be minus 1/2. So, I know that's a lot. This is a video. Go back and rewatch it if you need to. Look through the book if you need to. We'll also be working on this in class next time, but I want you to get this all down in your notes so next time we can just move with it. So, using these quantum numbers, we can come up with electron configurations. And what are electron configurations? Well, they tell us where the electrons are around an atom. How many electrons do we have around that atom? Now, while we're doing this, remember that typically the number of electrons is going to be equal to the number of protons. In fact, for every case right now. Later on, we'll see some things called ions that are going to have more or less electrons. But right now, how many electrons does it have? Equal to the number of protons. How do we know how many protons they have? For that, we go to the periodic table. Okay, let's consider the element sodium. Its symbol is Na. So turn to your periodic table, find Na, sodium. And we'll look at it, and we'll see, oh, it's got an atomic number of 11, which means there's 11 protons, which means it's going to have 11 electrons. So we have to find enough orbitals to stick 11 electrons into. Where do they go? Well, there's 3 rules we have to follow. I know, more rules, more numbers. Get these in your notes. They'll become second nature to you after a while. They're not really hard rules. First one is something called the Aufbau principle. Lowest energy orbitals fill up. We're going to fill the 1 before we fill the 2. We're going to fill the 2 before we fill the 3. Let's leave it at that for now. It'll get a little bit trickier next time in class. Second rule, the Pauli exclusion principle. Two electrons cannot have the same quantum numbers. That's just what we were saying earlier about the spins have to be opposite to each other. And three, something called Hund's rule. Looks like it got a little bit cut off here, but what it basically says is that orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second electron. Right now it's just words, I know, which means we're going to have to practice it, okay? So let's turn to a practice area here. Okay, so I've got this set up, this little diagram here. I've got a box for the 1s orbital. I've got a box for the 2s orbital. I've got a box for each of the 2p orbitals, and I've got a box for the 3s orbital. Now, how many electrons can fit in each orbital? That's right, 2. So now we're going to go along and fill them in. I'm going to put, and how we're going to draw these is with arrows. I am not good at drawing. Let me get a slightly larger thing here. Okay, so I'm going to draw an arrow with a little arrow thing going up. This is typically how we draw these, or you can draw it as an actual arrow. I like drawing these little half arrows because it saves space. That's an up-facing electron, and since there's nothing else in the 1s, I'm also going to have a downward spin electron. Okay, that's 2 electrons, but the sodium, I've still got 9 more to assign. So I'm going to go to the next energy level. Going to put an up electron and a down electron. Again, these ups and downs refers to the magnetic spin, but that's only 4. I still need 7 more. So now I have to go into the 2p. That's the next most energy rich state, and I'm going to have to put 1 electron. But now where does the next one go? Hund's rule tells us it has to go here. All 2p orbitals have the same energy. We can't fill the next one until we fill the other. I like to think of it like a hotel. If you have 3 hotel rooms and you've got 3 friends, you're not going to double up. You're each going to want your own room until the other room is full. Now we can go back and put the ones that are spinning down. 1, 2, and 3. Let's count up. We now have 10 electrons. We need 1 more, so we'll go to the 3s, and done. We have now filled out an electron configuration for sodium. Huh, you're probably saying. And I know, it doesn't really mean much to you right now. We will practice these. In fact, you will be practicing some tonight on your own. Okay, almost done. Just one thing I want to say, there's 2 ways we can fill out an electron configuration. One is orbital notation. Orbital notation is drawing out the electrons just the way that you just saw. Electron configuration is a shorthand. It's a way of writing it out. Here's the electron configuration for sodium. It tells us in the 1s orbital, we put 2 electrons. In the 2s orbital, we put 2 electrons. In the 2p orbitals, we put 6 electrons, and in the 3s orbital, we put 1 electron. I want you to try a few on your own, okay? And you can check these in your book, actually. On pages 116 to 120, they've got all of these electron element notations. I want you to try carbon, sulfur, and neon on your own. Then things are going to get weird as we move down into the 4th energy level because things start to overlap. In class, we'll do those, and we're also going to talk about a shorter way of writing some of these called a noble gas configuration. I know this video was long. Thanks for listening. Just hang in there.